All right, we're going to finish our discussion of oscillations by talking about the pendulum. So first, we're going to do the simpler case of just the simple pendulum, where it's just a very light string with a mass attached entirely at the end. And then we'll move on to the case of a physical pendulum where we have a rigid body to consider. So as long as our oscillation angle is small, we're able to make this approximation that a pendulum is simple harmonic motion. And I think it's more illustrative why we have to make that approximation when we actually work out the math of this. We're just going to start with that. But realize that for small angles, this is a very, very good approximation. Show that for small angle oscillations of a pendulum, we get the period equation as 2 pi times square root of L over G. So to start, let's draw ourselves a free body diagram at this point right here. So, because the pendulum is hanging, we will be experiencing a gravitational force, and it's entirely directed at the location of the pendulum bob, because we have a massless string here. And also, we do have a tension force that's going to be acting up there. So because we're dealing with how the angle changes, for a pendulum, we're actually going to set up a net torque equation to show what's happening in the rotational side of things. So to do that, we're going to want to set up a net torque equals I alpha equation. So net torque equals I times alpha. So let's figure out what the net torque is. So for the net torque, it's going to be equal to the torque caused by the tension force plus the torque caused by the gravity force mg. And again, we will just label these. So this is mg, and this is ft. So now we have to figure out what the torques are from this. So the torque from the tension force is 0, because it is directed exactly towards the pivot point. So again, if we're rotating around this point right here, R cross F is 0 because we have a force that's exactly parallel to our displacement. So the tension torque is 0. And for mg, we're going to use what we typically do with mg and use the lever arm definition of torque, where we can just take the lever arm and multiply it by the force. So again, the lever arm is the shortest perpendicular distance from the line of action of the force to the pivot point. So I'm just going to extend my line of action up. So since mg is vertical, we're just asking what is the shortest horizontal distance from the pivot point to the line of action. And well, if that's theta, this is theta. And if the length of the string is L, that means that we're after this side up here, which is going to be L times sine theta because it's across from theta. So that means that our lever arm is going to be L sine theta. So our net torque is going to be in the negative direction because it's going to decrease our angle. It's going to be equal to L sine theta times mg. So now we just set up the net torque equation. So we have net torque equals I alpha. So negative mg L sine theta is equal to, well, we have a point mass. So the entire mass is a distance L away. So we just use the moment of inertia of a point particle and then times alpha. And now we just see some cancellations hopefully happen. Well, first, we have an L here and an L here. So one of the L's cancels out. The mass also cancels out. And then after dividing by the other L, we get alpha is equal to negative G over L times sine theta. And writing that in differential equation form, we get d squared theta dt squared is equal to negative G over L times sine theta. But now we apply the small angle approximation, which for small pendulum angles, we can say sine theta and theta are basically the same. So we get d squared theta dt squared is going to be equal to negative G over L times theta. So that's our differential equation for the pendulum, but that's not entirely what we wanted to show. We wanted to show actually what the period is. So the fact that we know, coming back here, that omega is going to be square root G over L, because that's the square root of the number in front of our theta. Well, we know that period is equal to 2 pi times 1 over omega, which is equal to 2 pi square root L over G. And that's our answer. A grandfather clock can be modeled as a simple pendulum. On Earth, the pendulum completes one oscillation each second. When the pendulum is moved to the moon, it completes one oscillation in 2.45 seconds. What is the approximate value of acceleration due to gravity on the moon? Well, turns out we have an equation for pendulum period now. So we have that t is equal to 2 pi square root of L divided by G. So with any time you're doing this sort of comparison question where you do something, change it, and you're given the change, you should set up a ratio. So t on the Earth is equal to 2 pi times the square root of the pendulum length times G on the Earth. And then t on the moon is going to be the same thing, except with a different G value. And it's the same pendulum, so we actually can use the same length. And with all ratio questions, to really see what's going on, we're just going to divide both equations by each other to get a ratio. So we get the Earth period divided by the moon period is going to be equal to 2 pi square root L over G of the Earth divided by 2 pi square root L divided by G of the moon. And several things cancel. So 2 pi's cancel and the L's cancel. So we get time on the Earth divided by time on the moon is equal to just a big square root 1 over G on the Earth divided by 1 over G on the moon. And now we'll plug in some values and get going. So we'll also see that this could just simplify to the moon's G on top and the Earth's on the bottom. But so time on the moon was 1 second. Time on the moon is 2.45 seconds. And that's just going to be equal to the square root of 1 divided by 10 meters per second squared divided by 1 divided by G on the moon. So after squaring and rearranging, we get G on the moon is going to be equal to 1 divided by 2.45 quantity squared times G on the Earth, which is approximately equal to g on Earth divided by 10, or sorry, divided by 6. So this thing right here is really close to 1/6, because g on the moon is also very close to 1/6. So g on the moon is roughly 1/6 times g on the Earth, which is like 1.6 meters per second squared. We can also use energy for pendulum systems, just like we used it for the mass spring. This time we just got gravitational potential instead of spring potential. But the only tricky part with this is that defining the height can be a bit challenging. So this is what we call our h equals 0 point. So this is our u equals 0 is at the bottom because there's no gravitational potential. It can't go any lower. So we have to define how high up the bob is from this location at any time. So it's L below the ceiling at this spot, and it's L cosine theta below the ceiling at that spot. So the height change is just the difference, L minus L cos theta. That's how you get height of the pendulum, which you've probably seen before. All right, so now we got an example of just a pendulum simple harmonic motion. So a pendulum's motion is described by this equation. We want to find its amplitude, angular frequency, all that stuff. So to start, realize that since this is simple harmonic, we are able to just write the sort of parent equation here. So we have an amplitude times cosine times angular frequency omega times t plus the phase shift. And we have all these values. So we know that the amplitude is just going to be 0.2 radians. Because that's the number in front. And we know that the angular frequency omega is just going to be 0.4 radians per second. Because that's the number in front of the t. It's in the argument of the cosine. Then the frequency of the pendulum, well, we know that omega is 2 pi f, which means that the frequency is just going to be omega divided by 2 pi, which is going to be equal to, after plugging in, 0.0637 per second, which is the same as a hertz. Because again, this is units of cycles per second. So, well, if that's how many cycles we have per second, the period is just 1 divided by the frequency. And that's going to be 15.7 seconds. So then for the length of the pendulum string, what we have is you can use any of these equations relating to the length, but it's probably easiest just to use the fact that omega is equal to the square root of g over L, which means that omega squared is equal to g over L. So L is just going to be g divided by omega squared, and we get a very large value for a pendulum of 62.5 meters. And then we want to use energy to solve for the speed of the pendulum mass as it passes through the equilibrium position. So we are going to use the fact that energy is conserved in the system during the swing. And it's probably easiest to just set the maximum kinetic energy equal to the maximum potential energy. Because at the point where it has maximum potential energy, it's stopped, and the point when it has maximum kinetic energy, it's has no gravitational potential. So we can just set up an equation that looks like 1/2 times mv squared at the max value is equal to m times g times h at the max value. So this is the height above the equilibrium position. So based on our argument before, the challenging part with this is actually being able to figure out what the height change is. Well, when the string's at the bottom, the bob is a distance of L below the ceiling. And then when the pendulum is at an angle of theta, it is a distance of L cosine theta below the ceiling. So the difference in these two quantities gives the height above equilibrium. And that's why we had that interesting looking formula for gravitational potential energy for a pendulum. But we can see the Vmax, it is just the typical square root of 2 times g times h formula that we've used many times before, except the h value here was kind of challenging to get. But evaluating this, we get pretty close to exactly 5 meters per second. So again, we just have to actually go in and realize that the L minus L cos theta is there to get the height change. Lastly, we're going to talk about using a pendulum, but for physical objects, so things with shape, where we have to take things like center of mass and moment of inertia into account. So all we're doing is same idea, except we're pivoting a object instead of just a pendulum bob at the end of a massless string. So we're going to go through derivation again and say that if we're pivoting an object at the top with moment of inertia I up here, that's uniform, we can get this expression for the period of the physical pendulum. So this derivation is going to be quite similar. So here, we actually only have one force of note. We just have the mg force that's acting at the center of mass, which is actually exactly in the center in this problem. We also do have this like force caused at the pivot point, this hinge force that we've been calling it in the torque unit. But we're going to ignore it because it has a lever arm of 0, so it's not going to affect our angular displacement at all. And this is, of course, mg. So we're just going to do the same thing. So we're going to set up a net torque equals I alpha equation. And this one, it's just going to be the torque caused by mg is the net force. And it's going to be in the negative direction because it's a restoring torque. And we're going to do the same thing where we just take R perpendicular times mg. So we're just finding the lever arm here. And well, for this one, we see that since we're going to the center of mass, this distance right here is L over 2 because it's halfway across the rod. So therefore, this lever arm right here is just going to be L over 2 times sine of theta. Just using our lever arm method, because again, if the force is vertical, the lever arm is horizontal. So we're going to find the horizontal distance. So we get negative L over 2 sine theta times mg. So that's equal to I alpha. So negative mgl over 2 sine theta is equal to the moment of inertia, which we're just calling I, times alpha, which is the second derivative of theta with respect to t. So after rearranging, we get d squared theta dt squared is equal to negative mgl over 2I times sine theta, And then after applying the small angle condition, we get d squared theta dt squared equals negative mgl over 2I times theta. But we want to get the period out of this. So we know that omega is going to be equal to the square root of the number in front of the theta. So therefore t is equal to 2 pi times 1 over omega, which is 2 pi times square root of 2I divided by mgl. And notice that is exactly what we are trying to show. Okay, why limit ourselves to just pivoting at the top and the center of mass? Let's show it works for anything. So, if we're doing a different setup where this is our pivot point and this is our center of mass, the derivation is actually nearly identical. So there's our mg. Here's its line of action. And our pivot point is given by the dot. So that's going to be our distance. So the actual distance that the force is applied is given by d. And once again, this is theta. So the horizontal distance, which is just our lever arm, is going to be d sine theta once again. So this lever arm, because it meets our force at a right angle, is d sine theta. So we're just going to skip some steps and go through the net torque equation pretty quickly this time, because this is like the third derivation. But the net torque is just going to be equal to negative d sine theta times mg, because this is our lever arm, is d sine theta. So we know that negative d sine theta is equal to, or sorry, times mg is equal to I alpha, or alpha is equal to negative mgd over I times sine theta, which is approximately the same as d squared theta dt squared is equal to negative mgd over I times theta. So this implies that omega is the square root of mgd over I, which means that the period is equal to 2 pi out in front and flip it. And this I was taken about the pivot point. All right. And one applied example of this would be, suppose we are nailing a disc to the ceiling and we're going to displace it a bit and let it oscillate. We want to find the period of small amplitude oscillation. So first thing, notice this is exactly this, just with a different shape. So we can definitely solve this. We don't need to redo the derivation. The period is just going to be given by this expression we just derived. But I chose this example because there's something a bit tricky with it that I want us to look at. So the challenge here is that this is pivoted at the ceiling point. So this is our pivot location right here. It is not the center of mass. So this is where our gravitational force will be acting, generating a torque. It might not be as visual right now as to how that happens, but because it's at equilibrium. But again, if we think of our hoop getting moved a little bit, we are going to have an off-center gravitational force happening. So what we will have is something like that. So we need to figure out what D is and what I about the pivot point is. So we are given that I about the center of mass is equal to 1/2 mr squared. That is not where we're pivoting. So that's the I value here. So that means we want the I value there. And since this is a disk, that's just a distance of r. So if you're ever converting between moment of inertia values, it's probably using the parallel axis theorem, which says that the new I value is equal to I through the center of mass plus md squared, where d is the shortest distance between the two axes. So 1/2 mr squared plus another mr squared, because the distance between the two rotation axes is just r. So we actually get 3/2 mr squared as our I about the pivot point. So that means that what we have to do now is figure out the distance that the torque is applied, and that's just going to also be r, because the center of mass is r away from the edge of the disk. So we're just going to evaluate this expression. And notice we do get some cancellations. We get the m cancels, we get one of the r's to cancel, and we do have something that looks like the period of a pendulum, because we get square root. We get the square root of a distance divided by g. And working this out, we get about 1.72 seconds for this disk to oscillate back and forth. So I like this as a concluding example because we do actually have to use the parallel axis theorem, because we're pivoting about the edge, not the center, which we do so often. And that's about all I could think of in terms of just oscillation practice.